Great. Thank you so much, Karen. It's so nice to be back. As Karen said, I graduated in 2018 and worked very closely with Margot as well as Louise, and we had a lot of fun devising numerical methods for the degenerate porous medium equation, in particular trying to understand the strange behavior of these finite volume methods with harmonic averaging, and showing how we could resolve this and understand why that was happening in comparison to arithmetic averaging. I joined Amazon shortly after in the time series forecasting team. And today I wanted to come back and discuss the intersection of computational mathematics and industry. In particular, how I used a lot of the ICME skills in my current role and various projects. Here's an overview of my team at Amazon as well as collaborators. So this is joint work. We are split between Berlin and Palo Alto parts. So we're led by Tim Janikowski as well as Yu Yang Wang. And Young Suk Park is also a recent hire who's also a Stanford alum in EE. So what do I think are the core skills that ICME has in its foundation that is applicable in industry as well as in national labs and academia? Well, you see here I have an equal weight pie chart. And what we have is numerical optimization, statistics, and numerical linear algebra, where we see power ML and are at the basis of machine learning as well as deep learning. Also, what you need is some numerical analysis. So Karen mentioned physics-based modeling. We'll see how that can come into play here, as well as floating point computations. You need a rigorous background in how do you take a theoretical formula and be able to implement that in production with floating point computation considerations. The last part I have here is algorithms. How can we develop scalable algorithms in production as well? And these are, I think, the 5 core skills that ICME has instilled in us. So what I wanted to do today was go over 4 projects that I've worked on at Amazon, and you can see how these skills come into play across the board here. In the first one, GlueMTS, this is an open source deep learning time series library that we built based off of neural time series modeling. And this gets into the scalability, algorithms, and design part. Second was one of the first algorithms that I worked on when joining Amazon, which was deep factor models. So here we'll see some statistics and linear algebra playing a role. The third part of the talk will be AutoODE, which is a method that I worked on with my intern, Ray Wang, last summer, where we were tasked with how can we do COVID-19 case forecasting. So we went back to more of a classical ODE approach here. In the last part of the talk, I wanted to also discuss explainability for time series. In particular, since we're using deep learning models, they're known to be a black box. So how can we break this down? And you'll see that this actually reduces to a linear regression problem, where we can use simple least squares solvers and some numerical linear algebra here as well to compute this in production and give some explainability to the user of what is the model actually doing in practice. So to start things off, I wanted to go into the problem definition. So what problem are we trying to solve here? You'll see that we're trying to compute the probabilistic forecast. So we're trying to compute the given quantile forecast. What are we given? Here's a time series ZT. We know all of its historical values to the left of this vertical green line here. What we want to do is predict its future values. In particular, we're given its historical values, and you can also think of having a set xt of these feature covariates, which in this case are known in the history as well as in the future. So an example of the time series could be energy consumption in a household. You can also think of the retail case where ZT would be demand and XT could be promotion or holidays. So our team is focused on solving the first problem here, but you can think in practice that what we want to do is use this forecast to make optimal decisions. So here, what we want to choose in the end, in the supply chain case, would be choose the best action that minimizes the expectation of this probability given the future values. So this is where we can get in to some reinforcement learning methods here, which are also interesting. So a bit of the history of time series forecasting and when deep learning started playing a role here. So you see back already in 1969 in weather forecasting models, we're using some type of linear neurons as well as backpropagation in the 1980s. So this continued until the late 1990s, where we were using feed-forward models to forecast the problem for a single time series. The M3 competition in 2000 is a classical forecasting model competition similar to Kaggle. What they declared it was that simple statistical winners seemed better than these deep learning models. So we see a similar trajectory of deep learning not really being applied to forecasting up until its revival in 2012, when AlexNet won the ImageNet competition. That's where we start seeing this deep learning revival with the advent of GPUs, as well as more high performance computing, which makes these models more data efficient. Then you'll start seeing sequence-to-sequence architectures being used in time series, as well as modern deep learning techniques of RNNs and CNNs, which I'm going to talk about in more detail here, are going to be applied to forecasting. What is the difference now is they're going to be applied across all time series. So given a large collection of time series, can we effectively learn global parameters to extract related patterns across related time series, rather than applying them on a one-by-one basis? Up until 2018, when the winner of the M4 competition was actually a combination of neural network-based approach with classical techniques. So the steep factor model that I'm going to talk about fits into this category, where we're combining global and local models together. So that brings me to the first part of the talk, which is the GlueNTS library, and how can we solve the forecasting problem. So here you'll see the main design principles of GlueNTS. So this is a library that's built for researchers to be able to benchmark new time series models against state-of-the-art models. So one of our main principles is reproducibility. In particular, can you rerun the experiment and do large-scale benchmarking? Second one is scalability. In most of these problems, the time series data sets are very large. So in particular, we use streaming to be able to cache the data sets with Python iterators in the library. And the third part is modularity. So following the convention of other SciPy ML libraries, what we define is an estimator, which has a corresponding train routine, and that will output a predictor with a corresponding predict routine, which will then output these probabilistic forecasts. Here is our paper where we proposed the method, which was published last year in the MLOS part of the Journal of Machine Learning Research from our team. And here's the GitHub link if anyone wants to try out some of these models. On this slide, I show how you can use these modular components in GlueNTS to build some of the in-house models that we have and that our team has developed. So in particular, we have a distributions part, which is actually a collection of statistics distributions. So we have student T, Gaussian, and beta distribution, as well as discrete distributions available, such as negative binomial, binned, and also piecewise linear. Second part that's available is probabilistic components. So within here, we have stochastic models, such as linear state space models and Gaussian processes. And then we can use the gluon neural network built-in structures that you'll see here. So how can we build DeepAR? Which is a model that was built by my team. It's called Deep Autoregressive. So autoregressive models are actually taking in the prediction at the prior time point to predict the next time point, and then applied recursively. It's a parametric model, so you specify the given distribution. And then here we have, it's a canonical network. So canonical, we'll go into a bit more detail later, means that it's one-to-one. So we have one node going to one hidden unit, with the corresponding neural network component is just a simple LSTM. Second class of models, which was developed by another team at Amazon, this was called MQRNN. This was in the retail team. Here instead, what they do is they directly model the conditional quantile distribution here. And instead, it's using a sequence-to-sequence structure. So we have many nodes going to many hidden units. And we in particular have an encoder or decoder. So you can have a RNN or CNN encoder, which is going to an MLP decoder. The last two models that I highlight here are more of a combination of these local to global models. So Deep State, what it's doing is it works on Gaussian distributions. In particular, it's learning the parameters for the state space models through an RNN. And Deep Factor basically is another local global approach, where here you can think of the local model in this example being a Gaussian process, but it could also be any type of stochastic process that you define. So what are these probabilistic components in more detail that we have available? On the left, you'll see linear state space models. So these are more classic time series approach where we see the dynamics being driven by this transition equation here, where you have the probability of LT given the latent state LT minus 1. And then you're using that to compute the probability of ZT given LT. So in this case, the classical statistical models such as ARIMA and ETS can be put in this framework for a given set of transition dynamics. It's currently supported in the library through the Kalman filter. On the right, you'll see a Gaussian process. So this was one of the first projects that I worked on when starting, was actually implementing Gaussian processes for time series. So what do we have here? We have 5 blue data points, as well as the samples drawn from the predictive distribution. And the gray uncertainty region here is plus or minus 1 standard deviation of the predictive standard deviation. The reason I was interested in GPs when I started was actually the numerical linear algebra behind them. So what you can show when you're trying to estimate the log likelihood function is that it reduces to a linear solve of this kernel matrix. So you can define, this is the radial basis function kernel, which is an exponential distance-based kernel or a periodic kernel. And what you have is a linear solve of that with another right-hand side vector. In the likelihood, you actually need to compute the log determinant of this matrix, as well as its trace. So one way to do this would be to use some CME 302 techniques, such as just doing a Cholesky composition once, and we can factorize the matrix into LL transpose. This really simplifies the log determinant term, because what we can do is show that that is actually equal to just the sum of the log of the diagonals of L. By looking at the determinant of a lower triangular matrix is just going to be the product of its diagonal entries. So that simplifies that part, as well as the corresponding linear solve. However, in practice, Cholesky can still have numerical issues if the matrix loses positive definiteness. So we had to add a jitter term to the diagonal. One thing that interests me in this work as well is, what if we didn't want to use direct methods because they're not scalable, and also we don't want to store the matrices? Another approach, which was done by Andrew Wilson's group, is called GPyTorch, where they actually look at using conjugate gradient and Lenchos-based approaches here, which was really interesting for a more scalable approach. In particular, how they compute the log and the determinant of the kernel matrix is by storing the Lanczos tridiagonal matrices up to TP, and then taking the corresponding eigendecompositions of those tridiagonal forms. So behind a lot of these traditional ML problems is really powering linear algebra. Back to some of the forecasting models of the deep learning ones. On the left, here's an example of the canonical one-to-one network. So this would be an example of DeepAR here. We have one node going to one hidden unit, which is going to output one future time point. So we need to basically apply this method recursively to compute all the time points in the forecast horizon of tau. In contrast, you can have the sequence-to-sequence model. We have many nodes going to many hidden units, and we're directly outputting all the time points in the forecast horizon by directly solving the quantile regression problem. So what is DeepAR in more detail here? So again, we have this one node, which is our feature covariant at the future time step, as well as the past target time series value going into this head-in state, which is going to estimate the conditional distribution YT. So in this case, we're using DeepAR with a Gaussian likelihood. Well, if we have Gaussian, that means the next step of YT is going to be to estimate the parameters, so the mean and the standard deviation. And how do we do that? It's just a standard maximum likelihood estimation. So getting back to CME 308, where we compute the MLE for the unknown parameters of the distribution, which will give us our final output ZT. So you can also think about DeepAR with splines to make it go distribution free. Let's say you want a more flexible form where you don't want to specify the distribution. In particular, we can directly model the conditional quantile function instead of using parametric distributions. And this was led by Jan Gaustos on our team. What they use here is just a simple piecewise linear spline interpolation. So it gets into function approximation theory. And then for our sequence to sequence model, I mentioned you can have this other approach here where basically we have an encoding sequence as well as a decoding sequence. So this is basically solving the problem of how well does the prediction reconstruct the decoding sequence conditioned on the encoding sequence. And you can think about this as being conceptually close to multivariate regression. This is another project that I led, was bringing this algorithm from GlueNTS to production in Amazon Forecast. And one thing that was interesting about it is it allows for features to have different lengths. So because we have a separate encoder, we can actually allow for features that only have historical data points and are not known in the future. Another nice thing about this approach is that it's directly solving for the quantile function. So what is this quantile function? You can think about it as the inverse of the CDF. In particular, one thing that's interesting that we're looking at now is we're trying to ensemble these quantile forecasts. So let's say we have these quantile outputs. How can we ensemble them together using averaging or median approach? Another paper that was done by Jonas Müller was called Deep Quantile Aggregation. And what they show there, I found an interesting connection, partly to my thesis, was they show that if you're doing an averaging of the PDFs, that's equivalent to arithmetic averaging on the distributions. However, if you're taking the average of these quantile forecasts, just by using the derivative of an inverse, what you can show is that's equivalent to using the harmonic average on the distribution. So these different ensembles will have different properties. In particular, when you're looking at averaging the quantiles, since it's really a harmonic distribution of the PDF, you can show that the tails are actually smaller. So again, with this type of mathematical background, you can show different properties and be able to explain what is actually happening and what is more desired for the given situation. Another thing that we used here for interpolation as well was one limit of this approach is it requires that you train on the quantiles. So let's say that we have a new query quantile to estimate at the end, that would require retraining this model. So this is something that Youngsuk looked at when he started, was how can we remove this retraining limitation? And again, the solution was using simple function approximations. So we did a linear interpolation of the output quantiles on the interior, coupled with exponential extrapolation at the tails. Lastly, I wanted to discuss those more hybrid models of deep state and deep factor. So on the left, this was the deep state paper, which was proposed by Siyama on our team at NeurIPS in 2018. The idea here is to parameterize a linear state space model by an RNN. And here you'll see the latent function psi. Then the last layer, which is going to be the parameters of your state space model, is given by this affine transformation. And you can feed these theta parameters into your stochastic state space model. The difference here is that they're learned across the entire data set rather than one time series at a time. And we saw that performing better in practice. On the right here, you'll see the deep factor model that I'll go into in more detail in the next part of the talk. But here we have these deterministic nodes, GT. These are what we call global factors. And we'll see that these can actually be formulated in terms of some numerical linear algebra as well. So these are going to be the output from an RNN. And what we also have is this RIT, which is the local stochastic model. Both of these are going to be fed in to form our latent function and then used to estimate the final probability. The last slide I have here for GlueNTS is just showing the open source benchmark data set results. So we looked across multiple open source data sets and just profiled how the various algorithms were performing, again, for ease of experimentation for researchers to compare their models to other state-of-the-art models. So we also include the open source version of from Rob Hyman's ARIMA and ETS, as well as Facebook's Prophet, to compare to these methods. You'll see that across these data sets, there's no one method that's clearly dominating, which shows basically that in time series forecasting, you do need ensembles or a large collection of models. So these were the results in our paper here. Okay, and the next part of the talk, I wanted to discuss what these deep factor models were. In particular, one of the first algorithms I started on when I started. So here, what do we see is we've seen so far that these modern deep learning models can handle the operational forecasting problems well. So here we see, what if you have a cold start problem where there's no prior history? Some of those local statistical models may not perform well in this case. So the challenge here may be to predict the demand for each problem available at Amazon, where we have a large collection of items. The time series can be irregular, as you see here. Some have a long history, some are short, and some have none. It's only when combined do they have enough history and exhibit clear patterns. So this is where you prefer to use a complex global deep learning model. In contrast, what we can see here is that these modern methods struggle with strategical forecasting problem. In particular, there may not be enough data available for training. And you may need assumptions on the long-term behavior to be handled properly. In this case, you would like to use a local classical model, such as ARIMA or ATS, or a local state space model, especially if you have significant amount of history. And this is also better for getting uncertainty estimates. But the idea here is, what if we want the best of both worlds? Why do we need to choose between a global deep learning model versus a local per time series state space model? So here we can use some simple statistics to show the following decomposition. So what we have here is, let P be a distribution over exchangeable time series, meaning that the ordering does not matter, and over Z with link capital T. Then P emits the following form. You'll see that can be written as the integral of this product. So here what we have is the product over these local terms, so P of ZIT, where Z is the ith time series, given its past history, as well as this global term here involving GT. So this shows that the joint distribution can be written as a local global model. In particular, how can you prove this? You can first show the Di-Finetti theorem to show that the probability of Z is going to be given by the integral of the probability of P of Z given G times the probability of G, using the latent state. And then what we can do is apply the chain rule in the causal direction to get this term, as well as the chain rule on G. And you'll come up with this nice local global decomposition, which generalizes well. You can actually show the corresponding result for trees and hierarchical forecasts via the tree Di-Finetti theorem. So this is one of the results in our deep factor paper that was published in ICML in 2019. So how can we use this result and application of the chain rule in practice? Well, what we develop here is a family of models called deep factors. In particular, it's a novel hybrid global local model. What we do is define these fixed effects GT. In particular, these are linear combinations of K latent deep factors, GKT. And these deep factors are actually the principal components or the dynamic eigen time series. So this gets back to our classic SVD decomposition. And these are actually going to be output from K different RNNs. Then we add this attention term, WI, which is going to be a weighting of these different factors. So this is just a weighted linear combination of the eigen time series, is this first term, which we're going to call the global fixed effects. These WI are the local time series embeddings. So we see the input features going in to get our global model as well as our local model. So the random effects to model the uncertainty are given by these RIT. In the example here, you can model them as a Gaussian process with kernel Ki or a linear dynamical system. We also model zero mean Gaussian noise process using an RNN. So those are different instantiations of this family of models. When I started, I focused on the Gaussian process part here, in particular, as I said, because I was interested in the numerical linear algebra behind it. Then in the end, you can build this latent function, which is the sum of the global and local model, and compute the emission probability ZIT given the latent function. So how do we do the inference and learning for this model? Again, you'll see that it reduces to using the MLE to compute the parameters in the global RNN, in the attention networks, as well as the parameters in the local model. So for instance, if you're using a Gaussian process, you'll need to estimate with an RBS kernel, the amplitude, length scale, as well as the noise. If you have Gaussian observation, you can actually have exact inference, which is shown in the below table here. So in the table, I show 3 instantiations of the family of deep factor models. DFRNN is going to be given by a zero mean Gaussian noise process. So here we can have RIT just being normal of 0 sigma squared. And you can write down the likelihood exactly in this case. Since it's zero mean, we need to shift by the deep factor Fi, and it's given by a product of these normal distributions. If you use DFLDS, then here you can show that P of Zi is just given by a Kalman filter. Similarly, in the GP case, you can show that you get the following multivariate normal distribution. So we're assuming a zero mean GP, which is why the mean is actually given by Zi minus Fi. And here you have the covariance matrix given by your kernel function plus the learn noise term here. In practice, like I saw with Gillespie, we did run into issues with this maintaining positive definiteness, even with the sigma squared I term. If you have a non-Gaussian likelihood, we derive a method to use variational inference in a variational autoencoder here. The results in this paper show that deep factor outperforms a pure RNN-based forecaster as well as state-of-the-art methods. So in this plot on the left, we show that our method is more sample efficient, as well as it has less variance, and the runtime is faster. You can show that it actually requires a smaller number of parameters to learn. On the right here, we plot the weighted quantile loss of P90 forecast, which is you can think of as a simple pinball loss function on several open source data sets. So from UC Irvine, we use the electricity data set, which models the energy consumption of different homes, as well as some traffic data sets here, NYC taxi, traffic, and Uber. Deep factor is given by the purple, so we can show that it's actually more accurate, as well as has less variance than DeepAR, MQCNN, and Facebook's Bayesian-based profit method. Okay, any questions so far on the first two before I go into the auto ODE method?
Maybe, Daniel, you didn't talk about cost. Can you sort of give a sense of the difference in sort of actual cost of the different methods?
In deep factors?
Mm-hmm.
Yeah, so the cost here would be given by actually these diagonal plots that you see here. So this is actually plotting the running time. The orange curve would be deep factor versus a traditional RNN. So what you can show by using this local global decomposition is that the parameters are actually, the number of parameters is a sum rather than a product. So you can actually show that it is actually more scalable.
Wow, okay, thank you.
Sure. But that is always the consideration that we need to take into play, is it's constantly a trade-off between accuracy and cost. Okay, for the auto ODE method, let's go back to our problem definition is, can we think of this problem in a different way? So in particular, what we want to output is actually a trajectory of points future in time. So can we think of using ODE-based methods here to solve this problem? So that's in particular what we looked with my intern Ray Wang last summer. This is a paper that will be appearing in the Learning for Dynamics and Control conference this June. This was joint work with him, myself, Christos Flautos, who's the Amazon scholar and professor at CMU, my manager, Yang Wang, as well as Ray's advisor, Rose Yu at UC San Diego. So here, how can we reformulate this problem? Let's say that Z is actually given by the following ODE. So we have dz dt is given by some function S with unknown parameters theta, and it can depend on Z as well as potentially U, which can be an unobserved variable at time t. And then for these unobserved variables, we have another ODE given by G of theta governing those, as well as our initial conditions. So our task here is, given the historical values from 0 to t, can we learn f of theta and g of theta to output z in the forecast horizon of length tau? So one thing that's different than traditional ODEs is we're actually given more than the initial condition. We actually know the values up until time t. So can we make use of this to estimate the parameters? First, what if we tried to apply deep learning models here? So some of the other deep learning models that we've been looking at here, you would not know any prior domain knowledge on F and G and try to estimate them from the data. So here we would be trying to learn some function h, given the history, that would output the future. This is one of the first things that we tried actually on this COVID-19 forecasting test was, can we just apply sequence to sequence or fully connected neural networks here? What we found is, as you would expect in learning dynamical systems, is that deep learning models do not generalize well, especially when you have distributional shifts, which was definitely occurring with the COVID-19 data. So two systems, simpler systems that we looked at to try to understand why this was occurring and if we could replicate this was the Lochner-Volterra equations. So these are typically used in ecology to model the population size of a species. So PI is given the population size of species I. We have an unknown parameter Ri, which is the intrinsic growth rate, as well as Ki, which is the carrying capacity. Aij is a matrix that denotes the interaction between species I and j. What you can see here in the system of equations is we just have a matrix vector product. So we can optimize the computation by thinking of how to also optimize the matrix vector product term, which we'll get to later. Another system we looked at was the Fitzhugh-Nagumo equation, so FHN on the right. And this was originally developed actually to model the interaction of an axon memory for SQUID neurons. So here you can see that X is denoted as the voltage across the axon and Y is the outward current. And what this is modeling is the reciprocal relationship between X and Y through this unknown parameter C. So what types of distribution shifts can occur that make deep learning models perform bad here? Well, we can see two cases that we look at in the paper. The first would be a distribution shift in the data. And the second could be a distribution shift in the parameters itself. So we define the interpolation task to formally be where the distribution of the test set is within the distribution of the training set. In particular, the extrapolation set would be the opposite. So now the distribution of the test set is not contained within the distribution of the training set. In this example here, I show where the parameters change range. So in particular, in interpolation, we keep the carrying capacity for LV within this uniform range. But in extrapolation, we change its distribution. And same with the parameter C. You can also think about doing this for the initial values as well, P0 and X0. So what you find is, if we look at, we find a common occurrence regardless of the equation, similar to what we saw with the SEIR equations for COVID-19. In the interpolation task, the deep learning as expected would do well, which are these plots on the left here. However, when we go to extrapolation, where these parameter values change distributions, they're not performing well. They're basically mimicking the training set. And this is a common occurrence in practice. So for COVID-19, for example, the recovery rate parameter could change distribution given by vaccination rates. Similarly, the transmission rate also changes frequently given social distancing and other government policies. So we need a method that's going to be robust to these parameter changes. So what we developed here was this auto ODE to bridge physics space, more interpretable models with these black box neural network models. So in this case, we're saying if we know a form of F, can we use our domain knowledge? So for COVID-19, use an epidemiology ODE, or in ecology dynamics, use Lochner-Volterra to first discretize the governing ODE. And here we use RK4. So getting into some CME 306 fun, which is a fourth order ODE method. And what we do is we're going to integrate all the past states using the ODE solver to get these estimates Z hat up until time t. Then the second step is actually just estimating the parameters by minimizing the loss function. So here's where we'll see some optimization coming into play. So what we do here, this is the L2 loss. Could also think about using L1 for sparsity, or in the paper, we actually look at the quantile loss. Is we estimate the parameters for each time step in the historical range by minimizing the estimates of RK4 versus the true values. So this reduces down to just an optimization problem to find these parameters. Then what we do with the converged parameters is just integrate with RK4 to compute the values in the forecast horizon. The way we implement this is within deep learning frameworks. It's actually a pretty simple implementation. What you can do is just mark these as learnable parameters, and all it's basically doing is using AutoDiff to estimate the derivative of the loss function, and compute these parameters using the ADAM optimizer. So that's summarized in the algorithm code from our paper. So we again initialize the unknown parameters randomly and discretize the historical states with RK4 to get our estimate Z hat from 1 to T. Then we minimize the forecasting loss with the ADAM optimizer to get our estimated parameters. Then using RK4, we can get the predictions and the forecast horizon. So this is going to make the model more robust to distribution shifts. So how do we apply this knowledge for COVID-19? Here we develop AutoODE COVID. So we're looking at in particular, these SU-EIR equations, which was proposed by Zhao's group at UCLA. So we have a system of 6 ODEs. On the left, we have unobserved states. So we have U is given by S, E, and capital U. So S is the number of susceptibles that you have in your population, and E is the number of exposed, and U is the number of unknown. So this system of equations is an extension on the classical SIR equations, which are commonly used in epidemiology, to be able to incorporate the intubation rate as well as the unknown states. We also have observed, which are going to be used to calculate the forecasting accuracy. These are the only ones that are actually recorded. So what is this? It's the number of infected, the number of removed, which is equal to the number of recovered plus death cases, as well as the number of deaths. And N is going to be the total population, which is the sum of these 5 states. So here we have a series also of unknown parameters. We have beta I, which is the transmission rate. What we found in particular with COVID-19, in most models, they keep this constant, that it's not constant. As I mentioned before, this changes with government regulations and social distancing. So we actually make this a piecewise linear constant where the parameters we learn are the underlying knots. We also introduced this matrix here, which is the state agency matrix. So I denotes all of the 50 US states. We are forecasting COVID-19 in the US. And this is going to be the learned transmission matrix across states. Again, you'll see similar to Volterra, a matrix vector product coming into play here. Sigma I is the intubation rate, and mu I is known as the discovery rate, and to model the number of uncertainties. Gamma I here is going to be given by the recovery rate. Little ri is known as the recovery to death function, where here we use a simple linear function to model this, since we saw for different states having different convex versus concave behaviors. You could think of improving the accuracy of deaths by using a more complicated function approximation here as well. So one fun numerical linear algebra trick that we did is, let's say, since we have to learn this entire matrix, here we use C in this case, which is the learned transmission rate among the 50 states. We define C basically to be what we're learning, and A is going to be the element-wise product of M times C, which is just essentially M is going to be a sparse matrix with a 1 if the 2 states are adjacent and 0 otherwise. But in general, what we use in learning these matrix approximations, same with LV for the interspecies, is we can use a low rank approximation here. So again, some CME 302 coming into play, we can set C is equal to B transpose D, where both B and D are in RK by D. And we would assume in general that K is significantly less than D in dimension. So what we have is we're going to have T column vectors in RK, which you can think for each I is going to be the local time series embedding. So this helps us have less parameters to estimate, as well as we can turn this matrix product into just 2 efficient matrix vector multiplications. In particular here, we can compute first Z is equal to DX, which is going to be NRK, and then compute B transpose Z. So effectively, for the 2 numbers that we care about for the computational complexity, we can bring down the problem from order D squared to order KD. And same with the storage, we're only having to store this matrix vector product here. So again, some common CME 302 tricks coming into play in practice where scalability is one of our main concerns. In terms of results, here we're comparing AutoODE versus a fully connected neural network in the state of Massachusetts for the infected, removed, and death cases at the end of August. What you can see is the red curve is AutoOD is more accurate, as well as has a smaller confidence interval around the true solution. And then lastly, we show this benchmarking table here, where we see AutoOD outperforming the neural network models. We compare it to the fully connected neural network, which is based off of DeepAR, sequence to sequence, even Transformer, and the 2018 NeurIPS paper, NeuralODE, where here they're actually looking at using the adjoint method, as well as some graph methods here. So this is a graph convolutional network and graph attention network. Versus the original SU-EIR developed by UCLA this past summer, where they estimate the parameters in a similar way, but do not take into account the spatiotemporal matrix A. What we show is that AutoOD is more accurate in terms of the infected and removed cases, especially with a large discrepancy from the neural network models in the summer. And in terms of deaths, the deep learning models are performing a bit better, which could be due to the choice of our linear function for R here. But the rest of the details of this are in our paper. Lastly, I wanted to have a bit of time for explainability for time series. So this is a project that we're currently working on right now, which I think is an exciting direction that has been also popular in the deep learning community. So back to our initial slide here, let's take another look at it. What if we want to predict, given the feature, its effect on the next time ahead forecast? So if you look at XIT here, a peak in that is corresponding to a peak in ZT as well in the target. For this related time series, you see that its peak is corresponding to a valley here, and the peak is corresponding to a peak here as well. So some are positively correlated as well as negatively correlated. And how can we measure this effect, the effect of this particular time point at a point in the future? So what we use here is actually the Shapley values to calculate the feature importance. And this was proposed in the Lundberg and Lee paper in 2017. So these are the classic Shapley values from game theory, in particular for solving a regression problem. What are they doing here? We're summing over all feature combination sets without the feature I. And this is the number of combinations here with the model of f of s including I and the feature set including I minus the model not trained on I with the features not including I. So f here is the set of all features, which would be the power set in the full case, and m is the cardinality of f. So how can we solve this efficiently? What they propose in the paper is to use kernel SHAP, and they define this kernel K here, given by the following formula. What they actually show is, and what's done in their open source SHAP package is you can show that this is just a weighted least squares problem. So again, getting back to some fun numerical linear algebra. What is this X matrix? So this is in R2 to the M, the number of power sets by the number of features that you have. And it's just a simple binary feature coalition matrix. In particular, if you think of a column of X, it has a 1 in that entry if that feature is on in the subset, if it's turned on, and a 0 if it's turned off. Okay. W is our weight matrix, which is diagonal, and it's given by the following kernel. So in the paper, they proposed the kernel given by this equation. This is something recently that Youngsuk and I were looking at as well. This isn't defined when Z is equal to 0 or M. So how do we handle this case? So in particular, what you can do is add in a constant C here. And what you can show is, and this is where some more mathematical expertise comes into play, is as C goes to infinity, you can show that the solution to this least squares problem is the classical Shapley values. In particular, we were able to correct some steps in their proof, which was pretty fun to do. And this kernel, what does it look like? It's inversely proportional to the binomial coefficient. In particular, what you can show is it's maximized on the boundaries as well as minimized at the subset size, the ceiling of the subset size divided by 2. And in particular, this can help devise some of the heuristic sampling strategies that are implemented in practice, where basically what they're doing is sampling all feature subsets from the boundaries. So you can think about sampling all feature subsets of size 1 that include that feature, and then all the samples that don't include the feature, so of size m-1, and then moving inward. Because we're going to need some type of sampling strategy to be able to implement this in practice. Then we have y is in R2 to the m. What is this? Well, this is going to be the term of the model with that feature turned on minus the model with a reference feature. And the reference can be 0 or the average value of these related time series. In particular, one neat trick that you can do here is you can actually write this as a vector in Rm, where all you say is it's equal to the actual feature value if I is in the chosen subset, and otherwise it's equal to the reference. So what we can show is that we'll have an analogous representation for this for an indicator function, which will allow us to reduce the computational storage. So it's great that we can write it as a least squares problem, but can we do more? In particular, one of the main concerns here is that least squares on this problem would be order of 2 to the 3m. And of course, in practice, we're not going to use the entire power set and have this exponential complexity. But the problem for the time series case is we need to map the time series problem to a regression problem. And m in this case is going to be very large, which would require the number of samples n to also be large. Why is that? Is we need to take the number of feature covariants we have times their length is what's equal to m here. And for long time series, that can be a very large. And for accuracy, we'll need to draw a large number of samples. So can we do something more here? It's a neat application actually of the Sherman-Morrison-Woodbury identity from 302. What you can show is that X transpose WX is actually going to be written by this simple form. You can actually just show that it's a constant ones matrix plus the identity. So J here is going to be given by 1, 1 transpose, which is in Rm. C tilde, we actually define the correct form for this as well, is going to be equal to C plus the harmonic sum of m minus 1 minus 1. Since we have this simple form for the matrix, we can easily compute its inverse in the closed form using Sherman-Morrison-Woodbury. In particular, you can think of u and v in the equation as being square root of C tilde times the ones vector. So when we invert it, the inversion term is just in R, and you're able to get this nice term in the denominator, 1 plus C tilde times the dot product of the one vector, or the norm of the one vector, which is in our m, which is just going to give us m. And we have this nice relation. Can we take this a step further? Yes, we can actually write down the closed form for the entire least squares product matrix here. In particular, what you can do is by the definition of matrix multiplication, we have this term. Now, W is diagonal, so that's going to nicely break up the second term here, where we get a WJJ in front, and then that means that we only have the X transpose LJ term surviving. WJJ is just given by the kernel term. And in particular, this kernel only depends on the size of the subset. So it actually only has m distinct values, even though it's in R2 to the m by 2 to the m. Basically, subsets of the same size have the same kernel weight. Okay, and now we can substitute in our form for the inverse to get this term here as well. So multiplying X transpose times I will give us this initial term. And then here we just multiply it by 1. So what do we have for this term? This is actually just going to be the column sum of X transpose. The column sum of X transpose is only going to be the number of features that are turned on in that subset. So you can write a nice matrix free form solution here, which is going to be the kernel times this indicator of just if I is in the subset Sj minus C tilde times the subset size. In particular, we can write the closed form for the entire expression for each Shapley value from I from 1 to m. It's just going to be the sum from j is equal to 1 to 2 to the m of the kernel times this term that we just found times yj, where yj can be effectively defined as on the other side as a vector in Rm. And you can use a similar trick for the indicator vector, which will just be for each m, you can say it's equal to 1 if I is in the subset. So in summary, what we can achieve using this closed form is we can take the complexity comparison to least square solution from order m to the 2 to the m, or let's say n, where n is the number of samples, and bring down the storage significantly to only order m here, which is in particular importance when implementing this in a large scale production setup. The next step here for us is going to be devising an effective sampling strategy. So we need to effectively sample these subsets either using importance sampling or variance reduction method. In conclusion, what I wanted to show through going through these 4 examples of projects I've worked on in industry is that computational math is ubiquitous. It's everywhere within industry and academia, as well as national labs. In particular, what I find through ICME is that we have a very specialized and unique core skill set. Typically, we're seeing a lot more applicants are very applied in deep learning and have the experience using the deep learning frameworks, but do not have a lot of the mathematical rigor and statistical rigor that you really need to analyze these approaches. In particular, our skills can be applied through a wide variety of applications, from physics to more retail-based applications. You also need to be strong in the computational optimizations necessary to implement the scalable algorithms, as I've shown through some of these projects. In particular, strong numerical skills and analysis are needed in the ML community. So a lot of times you don't see in the papers discussion of convergence analysis or consistency in these approaches, which I think is something that is strong in ICME students. I've also provided my email here in case anyone has further questions after today, as well as a list of the reference papers that I discussed in this talk as well. Sorry if I went a bit over, but I wanted to save some time for questions.
Thanks so much, Danielle. That was excellent. And of course, I especially love your references to CME 302, 306, and 308.
Yes, yeah. And throw in 304 for optimization as well.
And there you Excellent. We do have one question in chat. Is it practical to use higher precision floating point arithmetic to reduce the loss of positive definiteness?
Yes, so that is something that we definitely looked at in any method that required numerical linear algebra. Was we needed a higher precision. Whereas in the deep learning models, they were using single precision. We did try to use floating a double precision there as well. But we're still running into some numerical issues on the GPU, even with double precision.
And Mark has a follow-up here, higher than DP.
Oh, I did not try that, but that would be interesting to also try. A tougher cell because trying to increase the number of storage, but yes, that would be something to try here as well, especially if you're more interested in the numerical linear algebra research. Like I said, we implemented the jitter term, and in practice, I think that approach in GPyTorch of using Lanczos would be interesting to try, although with Lanczos, you do need to worry about losing the reorthogonalization term, which is another thing that I actually worked on with Michael Saunders when I was here in his class, was showing that Lanczos doesn't maintain numerically orthogonality. But that's something I think is unique in ICME too, is a lot of applicants I see sometimes have the applied background or sometimes are strong in the theory, but not really a mix of the two. And I think what we're really looking for is that mix that ICME provides.
Here's another question on slide 36. Should there be a W between the X, the T, and Y?
Yes, sorry, this is a correction. We should have the W right here. Thank you and good catch. I think I have it right on the next slide here. Yeah.
From an ICME student to another. So that's a pretty interesting catch.
You're just testing everyone, right?
Right, exactly. You know. No, thank you for that.
That's great. Any other questions?
Daniel, I have a general question on the explainability towards the end. Yes. So when you, and this is a general question, not very technical, but what is the objective of introducing explainability? Is it to confirm that your understanding of the algorithm is what it is, or is because it's demanded by perhaps users of the algorithm that they want to know more about what's happening behind?
Yeah, this has actually been a user request, actually. So a lot of the users are uncomfortable with using some of these deep learning models. And in particular, they're feeding in a lot of these feature covariance, which could be price, promotion, holidays, depending on the application. And they want to understand, is the model actually using this? And is the model making actual sense? So is it if it's a promotion, is it causing actually a positive point in the demand or not? So that's kind of the intuition here actually did come from the users.
Interesting.
I had a question and follow up to what Gianluca asked regarding costs.
Sure.
When you're thinking about costs these days in looking at, for instance, an RNN model, are you looking at the environmental costs along with other costs of what you're doing? Or I'm curious, I know that's becoming a bit of a hot topic, and how does that factor in?
No, that's a really good question. And that's where I think a lot of what we have in computational math is to try to actually speed up the algorithms and the math behind it rather than throwing a large amount of compute power at it. Because in that case, if you just go by the more data, the larger compute that I have, the better solution I'll have is, you're right, you can have those environmental consequences that are not ideal. So if we can come up with a more efficient algorithm, then we don't need to rely on this large number of compute, is typically one of our goals here. To reduce that cost as well. So that's something that we're looking at. Margot?
Yeah, I have a question. You know, Danielle, one of the things I like so much about your talk is how you connected what you've done to your ICME knowledge. And so maybe a logical question is, what was the biggest or steepest learning curve for you when you left ICME and started in this new field? And it would be really wonderful to hear a little bit more about how long it took for you to really get into this new field. And I know that the ICME courses helped you, but what were some of the things you learned in maybe somebody else who wants to follow in your footstep? What advice would you give them in terms of courses or other things to explore while they're still in ICME?
Yeah, no, that's a good point, because as you can tell, it's pretty far removed from my exact thesis area. So sadly, I don't have PDEs here. And it's not a direct application of numerical analysis. In particular, when I was at ICME, I took CS 229. So I knew more classical statistics and machine learning, but not as much on the applied deep learning. So this was something that I really kind of had to dive into when I started. So yeah, I may recommend more kind of practical deep learning classes as something that I didn't take, that I had to kind of learn, I would say, on the job. But I do think if you have the ICME skill set, it's easier to adapt to different problem domains. So at the beginning, it was nicer for me because my manager did know I was interested in numerical linear algebra. So he let me start with that Gaussian process project while I was ramping up on the kind of deep learning coding frameworks. But in terms of advice, I still think that having the core math skills with computing is what is actually used in practice and what is important. In particular, even taking our coding classes, the original CME 212 to 214, in particular, the GPU coding classes was another kind of unique skill that I saw other teammates not having as well, that helped me be able to implement things and faster and show my value in that way. Also, the team seemed to really welcome someone from a different background. And typically we do kind of weekly reading groups where you can present on papers in physics or PDs or whatever is more interested in your background. So I would say our group is actually pretty diverse. We have someone who used to be a pure math professor versus myself, more in computational PDEs. And then we have another person who's in computational optimization. So it's pretty diverse in that range. One thing that was nice in starting this job is it wasn't as much of a transition from ICME because it was still a mix of research with application together, which was something that I was looking for. But I would say definitely be cautious and ask a lot of questions in your interviews too, of if you're going to be able to still have the right to publish. Those type of things up front are good to know before going into industry, if that's something you value. Yeah.
Thanks for those words of advice, Danielle, and really appreciate you coming today. I see we're past the hour, so we'll close it there. And hopefully we'll share this with everyone, the videotaping afterwards, if others could not attend live today. So hope to see you back in ICME this fall.
Yes, I'd love to come back. I miss ICME a lot. I miss all of you. So thanks for having me.
Thank you, Danielle. Thank you.
Thank you.
Thanks, Gianluca. Thanks, Karen. Thanks, Margot.
Bye, everyone.
Bye.